Welcome to this session of Materials Engineering. Myself, Anirban Sarkar, Assistant Professor in Department of Mechanical Engineering of JIS College of Engineering, Kolkata. Today's session, we will discuss about the atomic bonding of materials. Learning outcome. After completing this session, we will understand the importance of material bonding and its classifications. We know that atoms are composed of electron, proton, and neutron. Electrons and protons are negative charged and positive charged particles, respectively. The magnitude of each charged particle in an atom is 1.6 into 10 to the power minus 19 coulombs. The mass of the electron is negligible with respect to those of the proton and the neutron, which form the nuclei of the atom. The unit of mass in an is called an atomic mass or atomic mass unit, which is approximately 1.66 into 10 to the power 27 kg, 10 to the power minus 27 kg, and which is equal to the 1/12 the mass of an carbon atom. The carbon nuclei has 6 number of proton and neutron. Neutrons and protons have similar masses, roughly equal to the one atomic mass unit each. A neutral atom has the same number of electron and proton. So while studying this atomic structure, a very important definition that is called mole need to be understood. A mole is the amount of matter that has a mass in grams equal to the atomic mass in atomic mass unit of the atom. Thus, a mole of a carbon has a mass of 12 grams. The number of atoms in a mole is called the Avogadro number, which is given capital N equal to 6.023 into 10 to the power 23, and it is known that one Avogadro, that is Avogadro number, equal to the 1 gram per 1 atomic mass unit. Most solids have atomic densities around 6 into 10 to the power 22 atoms per centimeter cube. The cube root of that number gives the number of atoms per centimeter. About 39 millions. The mean distance between atoms is the inverse of that, or that is 0.25 nanometer. This is an important number that gives the scale of atomic structure in solid. Now, in order to understand why materials behave like they do and why they differ in properties, it is necessary that one should look at atomic level. The study primarily concentrate on two issues, that is, what made the atoms of cluster together and how atoms are arranged. As mentioned, we know that atoms are bound to each other by number of bonds. The interatomic bonds are primarily of two kinds, that is primary bond and secondary bond. The ionic, covalent and metallic bonds are relatively very strong and it comes under the primary bond, whereas the van der Waals and hydrogen bonds are relatively weak and termed as secondary bonds. Metals and ceramics are entirely held together by primary bonds, that is ionic and covalent bonds. In ceramics, the metallic and covalent bonds in metals, although much weaker than the primary bonds. Secondary bonds are still important, although they are weak in nature. They provide the links between polymer molecules in polyethylene, which makes them solids. Without that, also, water would boil at minus 80 degrees centigrade. And life, as we know it on the earth, would not be exist. So while discussing about this atomic structure, that is, we know that fundamentals of atomic structure is required, since it is considered that atoms are the basic structural units of all engineering materials. Atom consists primarily of three basic subatomic particles, as we know, that is proton, neutron and electron. The current simple model of an atom is very small nucleus of diameter 10 to the power minus 14 meters is surrounded by a relatively thin dispersed electron cloud of varying density, so that the diameter is in order of 10 to the power minus 10 meter. The electron charge cloud thus constitutes almost all the volume of the atom, but accounts for very small part of its mass. The electrons, particularly the outer ones, determines most of the electrical, mechanical, chemical and thermal properties of the atoms. And thus basic knowledge of atomic structure is important in the study of engineering materials. The mass and charge of the subatomic particles, as we know, that is, it is roughly 1.66 into 10 to the power minus 24 grams, or if we convert into kg, that is 1.66 into 10 to the power minus 27 kgs. The charges are, for proton it is positive, that is 1.6 into 10 to the power minus 19 coulomb. Neutrons have similar mass of proton, but it is no charge. Electrons, which has negligible mass compared to the proton and neutron, that is 9.109 into 10 to the power minus 28 grams, and the charge is just opposite to the proton. So it is found that in an atom, the atomic weight, it mainly consists of proton and neutron, because electrons has very negligible masses compared to the proton and neutron. So in order to understand the atomic bonding in solids, why differ in properties, so one should know, look at the atomic level. The study primarily concentrate on the two issues as we have discussed, that is what made the atoms to cluster together and how atoms are arranged. As mentioned, that atoms are bound to each other by number of bonds. These interatomic bonds are primarily of two kinds, that is primary bond and secondary bond. The ionic, covalent and metallic bonds are relatively very strong and grouped as primary bond, whereas van der Waals and hydrogen bonds are relatively weak and termed as secondary bond. Metals and ceramics are entirely held together by the primary bond, that is the ionic and covalent bonds in ceramics, and the metallic and covalent bonds in metal. Although much weaker than the primary bonds, secondary bonds are still very important. They provide the links between the polymer molecules in polyethylene and other polymers, which makes them solids. Without them, water would boil at minus 80 degrees centigrade, and the life as we know in it on the earth would not be exist. Now the type of atomic bonding, it is primarily divided, as we know, into the two categories. One is primary atomic bonding and number two is the secondary atomic and molecular bonds. Primary bonds are again subdivided into ionic bonds, covalent bonds and metallic bonds, and secondary atomic and molecular bonds again subdivided into permanent dipole bonds and fluctuating dipole bonds. So first of all, we will discuss about the ionic bond. This bond exists between two atoms when one of the atom is negative, that is it has an extra electron, and another atom is positive, that has an lost an electron. Then there is a strong direct Coulomb attraction. Basically, ionic bonds are non-directional in nature. Now, for an example, that is sodium chloride. In the molecule of sodium chloride, there are more electrons around chlorine atom, forming, that is, chlorine negative, and fewer electrons around sodium atom, thus forming sodium positive. So these two, positive and negative, becomes a direct Coulomb force and they are bond together. Ionic bonds are the strongest bond. In real solids, ionic bonds is usually exist along with the covalent bond. Now in this figure, that it is this schematic diagram, it is shown the ionic bonding. Here sodium is giving an electron to the chlorine atom. Thus, the outermost shell of an sodium atom has only one electron, which is giving to the chlorine atom. And in chlorine atom, the outermost bond has only one less than the sufficient electron. So by interchanging one electron from sodium atom to chlorine atom, thus making sodium atom positive and chlorine atom negative. And now these two differently charged, that is positive of sodium and negative of chlorine, makes a strong ionic bonding together and thus giving a stable structure of NaCl. Next, we will discuss the covalent bonding. In covalent bonding, electrons are shared between two atoms to saturate the valence. The simple example is an hydrogen molecules where the electrons spend more time in between the nuclei of two atoms than outside, thus producing a bonding that is called covalent bonding. Covalent bonds are stereospecific, that is, each bond is between a specific pair of atoms which shares a pair of electron, that is opposite magnetic spin. Typically, a covalent bonds are very strong and directional in nature. The hardness of diamond is a result of fact that carbon atom is covalently bonded with four neighboring atoms, and each neighbor is bounded with an equal number of atoms to form a rigid three-dimensional structure. Now, in this schematic diagram of covalent bond, the hydrogen molecules are sharing electrons in between two atoms. So we know that hydrogen molecules have only one electron at outermost shell. So the two hydrogen molecules are coupled to each other. That means their two electrons are shared by the two atoms simultaneously, thus producing a strong covalent bond. Next, that is metallic bonding. Metals are characteristics by high thermal and electrical conductivities. Thus, neither covalent nor ionic bonding are realized because both type of bonding localized and valence electrons and preclude condition. However, strong bonding does occurs in metals. The valence electrons of metal also are decolonized. Thus, metallic bonding can be viewed as metal containing a periodic structure of positive ions surrounded by a sea of delocalized electrons. The attraction between the two provides the bond which is non-directional. So in this figure, it is shown that a metallic bonding, as metallic bonding are grouped together and there is an electron cloud to form the valency electron, and the atoms are simultaneously shared by various electrons, valency electrons together, and thus forming a very strong metallic bond. Next, that is fluctuating induced dipole bonds. Since the electrons may be on one side of atom or the other, a dipole is formed. That is the positive nucleus at center and electron outside. Since the electron moves, the dipole fluctuates. This fluctuation in an atom, suppose A, produce a fluctuating electric field that is felt by electron in an adjacent atom B. So atom B then polarized so that its outer electron are on the side of atom closest to the positive side or opposite to the negative side of the dipole in A atom. Polar molecule induced dipole bond. It is another type of secondary bonding exists with asymmetric molecules. Also, it is called polar molecules because of positively and negatively charged regions. A permanent dipole moment arises from net positive and negative charges that are respectively associated with the hydrogen and chlorine ends of the HCl molecule, leading to bonding. The magnitude of this bonding will be greater than for fluctuating induced dipole. So there are two kinds of bonds are also called van der Waals bond. Third type of secondary bond is the hydrogen bond. It is categorized specially because it produces the strongest force of attraction in this category. Now we'll discuss about that permanent dipole and hydrogen bond. As in figure, it is shown that dipole bound in water. So this permanent dipole bond or hydrogen bonding, it occurs between molecules as covalently bonded hydrogen atom. For example, CH, OH, FH, etc. It shares single electron with other atom, essentially resulting in positively charged proton that is not shielded any electron. This high positively charged end of the molecule is capable of strong attractive force with the negative end of an adjacent molecules. The properties of water are influenced significantly by the hydrogen bonds or bridges. The bridges are of sufficient strength, and as a consequence, water has the highest melting point of any molecules of its size. Likewise, its heat of vaporization is very high. So as shown in this figure, that is the example of an dipole bond in water. So a permanent dipole bond that is occurring in the water, so as that likewise its molecular size, it was the highest melting point, and its vaporization is also high because of permanent dipole bond or hydrogen bond. So these are the references is shown here, that is recommended books and notes are available. Material Science and Engineering by W.D. Callister and adapted by R. Balasubramaniam, that is Wiley, India. Material Science and Engineering by William Smith, Javed Hasimi, Ravi Prakash. Material Science and Engineering by V.D. Kodgiri and S.D. Kodgiri by Everest Publishing House. And Google Drive links are given so that one can see the notes of this materials engineering, and a book is uploaded by this W.D. Callister. So thank you for joining this session.